Welcome everybody to our Veolia Water Tech Talk today on managing peak wet weather flows. I can see we've got a couple people that are still in the process of logging on here, so we're going to give it just a few more seconds and then we will jump into our presentation today. Welcome everybody to today's webinar. My name is Jill Browning and I'll be the moderator for today's webinar on managing peak wet weather flows. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. First of all, hopefully you should be able to hear me speak at the moment, but I do want to mention that if you have any difficulties throughout the presentation today, that there are two different ways to connect to the audio. You can either connect through your computer or through a phone line. So should you have any issues, feel free to switch between those two. And also, due to the large number of attendees that we have on today's presentation, we have gone ahead and muted everyone's lines, but no worries on that. We still want you to be able to interact with our speaker. And in terms of interacting with today's presenter, you can ask your questions via the questions panel anytime throughout today's presentation today. And we do have some time set aside for questions at the end of the presentation. So feel free to go ahead, ask any questions that may come up or come to mind. And we will try to get through as many of those questions at the end of the presentation today as time allows. Today's webinar is also one of many in our upcoming Veolia Water Tech Talks program that is happening throughout this year. If you're interested in signing up for any additional webinars, feel free to check out our schedule over at www.veoliawatertech.com and register over there. And additionally, we've gone ahead and made available our collection of on-demand webinars that we've conducted over the last couple years as well. You can access more than 40 on-demand webinars, again, over at that www.veoliawatertech.com. So feel free to go over to the website and browse through the various topics and register for any of those that may be of interest to you. One other housekeeping note that we have here is a PDF participation certificate will be made available to you after the webinar. You should receive that within 24 hours or so, so feel free to keep an eye out for that and if that's something of interest for you. At the end of today's webinar, you will receive a quick survey requesting your feedback. Should take no more than 20 or 30 seconds or so. And for those of you who do complete that survey, you'll be entered into a drawing for a chance to win a $25 Amazon gift card. So if you would be so kind as to fill that out for us, we would greatly appreciate that. We do very much value your feedback. Now, before we hop into the main part of our presentation today, if you are not familiar with Veolia Water Technologies, we are a leading water and wastewater technology provider, and we offer our clients a variety of technologies, services, and projects. For more information, feel free to go over to the website to learn a little bit more. And we also support our clients through a variety of different markets, from industrial markets as well as the municipal markets to help support water and wastewater needs. So with that, now I'd like to introduce our speaker for today's presentation. Reed Staten is the U.S. Product Manager for Veolia's Active Flow Ballasted Clarification Technology. Located in Raleigh, North Carolina, he has a degree in mechanical engineering from North Carolina State University and has been with Veolia for over 20 years. Prior positions within Veolia include mechanical and process engineer and process manager. He has an extensive experience in process engineering and operation of physical chemical separation and physical processes for water and wastewater treatment. And with that, I would like to now turn it over to Reed for our main presentation today.
Thank you, Jill, and thanks to everyone who attended today. Hopefully you find this very useful. We'll go ahead and jump right in. Today's talk is really about how municipalities deal with the impacts and the challenges associated with wet weather. And we're going to talk a little bit about those impacts and challenges and highlight a few projects where municipalities have gone in and done their best to manage and minimize overflows as well as untreated wastewater entering the environment. So just a quick agenda. We'll talk about the impacts of obviously the wet weather. We'll talk about the various challenges that municipalities deal with. We'll talk about some of the solutions that they look at when they're going through their evaluation to put a plan together. We'll highlight a few case studies and then a quick summary. So, wet weather and what its ultimate impacts are. Obviously, wet weather flows are very unpredictable, very dynamic, and whether it's a combined sewer network or a separate or sanitary sewer network, the influx of stormwater essentially has the chance of overwhelming both the sewer network as well as the wastewater treatment facility. These backups, especially in the collection system, often result in backups into basements, into homes, to overflow into streets. In the course that can result in the discharge of untreated wastewater into our rivers and streams. From a wastewater treatment perspective, the flows that then make it down that collection system also have the same potential impact on the wastewater treatment facility, not only from a hydraulic perspective, but also the ability to effectively treat and potentially impacting performance even after the event for days or weeks following that event. Obviously, one historical solution for that has been to divert flows around the plant. And obviously there's a risk associated with that from a public health perspective. And so a lot of facilities, especially in SSO environments, we'll talk about some of the paths they take to mitigate that. Stormwater is a big player now as well, especially with impervious surfaces. Those that want to force more stormwater into our sewer systems, into our rivers. These stormwaters obviously are prone to collect oil, pesticides, fertilizers, you name it, trash, and either end up in the sewer or into the environment. And it's both of these overflow events that really drive home the impact associated with pathogens and microbial pollutants, but also with overflow events, there's the chance for an environmental impact as well. There's a level of nutrient loads that is associated with these overflow events, and while that's important from an aquatic ecosystem perspective, too much of a good thing can be a bad thing, and in this case, harmful algae blooms. As that dies, it decays, consumes oxygen, and essentially creates a hypoxic zone. And one of the largest in the world is actually in the Gulf of Mexico via the Mississippi River Basin. In addition, there's the economic impact associated with this. We talk about the ability to effectively treat from a drinking water perspective due to these contaminants, industries such as the fishing industry, but also recreation and tourism impacts as well. So jumping into the challenges that municipalities deal with, and managing these impacts are one of the largest and costly challenges that municipalities face. And they do this, with unlimited or limited resources as well, in terms of manpower, in terms of budgets. This things shrink on a daily basis, as we all know. So doing all this with limited resources is hard enough, but you tack on some of the other challenges that we'll talk about. Because of the impact of wet weather, obviously regulations are constantly evolving with the goal of eliminating those overflows and those diversions. It starts at the federal level. States can influence that, and so you've got multiple angles. Oftentimes those utilities or those permitting levels don't always agree or align, and then there's also a lack of clarity. And we look at the past and present regulations of where we've come from. You start back in 1972 with the Clean Water Act, and it really established our national pollutant discharge elimination system that we still use today. It prohibited SSOs, or sanitary sewer overflows, and it went out of its way to try to mitigate the risk associated with combined sewer overflows. It also pumped in a significant investment into the market to build that infrastructure to allow facilities to be able to meet the policies set forth with the Clean Water Act. In 1994, the EPA stepped in and established a CSO control policy. It really set essentially minimum criteria that would define when a CSO would be permitted by NPDES. It set a deadline of 1997, and it again defined, quote unquote, 9 minimum controls. And a lot of those are around maximizing the treatment at the wastewater treatment plant, obviously getting as much flow to the wastewater treatment plant as possible and treating it effectively. Obviously, from a sewer maintenance perspective, there was focus on operation and maintenance of those sewer systems as well, but also public notification in case an event did happen. And then it forced municipalities to focus on a long-term control plan for focusing on controlling those CSOs. In 2003, switching to the sanitary sewer side, EPA proposed a blending policy. It's much like the CSO policy. There were minimum criteria that, if followed, basically would deem that blending would not be considered a bypass. It was out for public comment. It received a lot of feedback, both sides of the table, in favor, against. But blending obviously is viewed as posing a great threat to public health. There were some concerns that if blending was allowed, it would undermine the incentive to focus on those collection system repairs and reduce I&I. But on the flip side, then, the infrastructure costs and the impact to high customer fees. So a lot of back and forth, and at the end of the day, in 2005, the EPA backed off on any further action and essentially declared that blending wasn't allowed, whether or not you're meeting permit. Of course, that went over really well with a lot of territories, and in 2013, the 8th Circuit Court of Appeals basically ruled against that, saying blending is not equal to a prohibited bypass. And ever since, the rulemaking has been in limbo since. Very little clarity. The EPA has recently put forth some talk about a revised draft ruling. They went as far as in 2014 holding a public forum with health experts, on the impacts of blending. Last I heard, this was supposed to be released for public view and comment in late 20. But given the climate of where we are now, I'm sure that's delayed a few things, and I'm not sure exactly where it stands, but hopefully soon there'll be some additional clarity to that. So switching to the infrastructure, focusing initially on the collection system. Obviously, as you can imagine, many municipalities, this is one challenging aspect that they deal with. And they're estimated over 8,000 miles of public collection systems and over 5,000 miles of private systems in the US. And one of the biggest challenges is the majority of these collection systems were built in the early 20th century. Up to about 50 or 60 years ago, that was dominated by combined sewers. And since then, perception and regulations have changed a little bit to drive it more towards a separate or sanitary sewer. But as you can imagine, over the years, due to the age of the infrastructure, that networks are complicated. They're often a blend of combined and sanitary, each dealing with and behaving differently with wet weather. And that's another aspect is, one means of dealing with a set of collection systems is likely going to be different for another set of collection systems. And many municipalities obviously service surrounding communities as well, and oftentimes they don't own and operate those collection systems. So there's a level of who's responsible for what and just coordinating that effort. And collection systems, while very important to be proactive and stay ahead of the problems, it's a significant drain on resources. No pun intended, but it is very costly, often seen as a never-ending endeavor. So all those things are, things that the municipalities have to figure ways around. Looking at the wastewater treatment side, obviously very similar conversation. Most wastewater treatment plants are reaching their end of life. Many of them are, 30, 50 years old. They've done some minor improvements over the years, but oftentimes they're undersized and just ineffective or very inefficient with respect to performance. Site constraints is another one. If a facility is looking to, expand or put new systems in, some facilities are just limited on their site constraints. And then wet weather versus dry weather. Plants are very efficient during their dry weather conditions. Wet weather is a completely different animal in a lot of ways. You've got the dynamics of the initial inrush of flow. Oftentimes that means the very high peak demands at the beginning of an event that can scour pipes, that can often resuspend solids that have settled over time. So not only do you get this high first flow, but you get an inrush of solids typically as well. And that can vary from one first flush to the next. And then you get the post-dilution on the backside as the event drags on. Usually the solids contaminants are diluted. And so you're dealing with two animals, essentially the front end and the back end. And that is completely different than how they're typically operating with the dry weather flow. So managing the plant during that time can be stressful, and dealing with, not only the wet weather during the event, but also the operation as you come out and transition back to our more dry weather flow. Talk quickly about urbanization as well. We kind of highlighted that, the increase of urbanization, the increase of impervious surfaces, especially with big cities. It basically just is increasing the amount of stormwater that enters our rivers, that enters our sewers. As I mentioned, that can lead to additional pollution as it picks up and runs across, roadways and what have you, but also climate change. Those two graphs highlight, really the change in frequency and intensity over the last, century. And the lower left-hand graph here is just the annual average of the continental United States as a whole. And what you see here is the line of best fit in terms of the increase, and over time we are seeing an increase in roughly 0.2 of an inch per decade. And then when you break it down from a kind of territorial perspective, the graph in the upper right looks at the last 30 years in terms of an annual average flow and compares it to the 20th century annual average flow. And as you can see, there are many areas in the US that are seeing 5, 10, even more % on an annual basis increase than they saw in the 20th century. So again, it's all playing a role, and it's complicated for municipalities to deal with. So now we understand the impacts. What are we looking at in terms of the solutions? Well, first and foremost, it starts with a comprehensive assessment, really getting into the weeds and understanding, where the failure points are, what's the likelihood that these points within the collection system of the wastewater treatment plant are going to fail, and then what their ultimate impact is going to be. And oftentimes that's process modeling, it's hydraulic modeling, and hiring a consultant and working with them. And at the end of the day, it's understanding not only what your projected peak wet weather flow is, but what can my collection system handle from a hydraulic, but also a treatment capacity perspective, and identifying where those weak points are. It also is, doing a deeper dive on the sewer and putting more monitoring means in there, modeling it as well to really understand the dynamics of that sewer during wet weather events to, again, help with that plan moving forward with respect to where do we need to focus on our improvements, where can I implement, additional control strategies to help mitigate and manage that flow. So all that info is important for, a plan and path forward. And then characterization of that real wet weather flow, taking data, what does the peak flow look like? What does the peak solid look like? How long does it last? What's my dilution factor on the backside? As much data as you can collect on a wet weather event, and multiple wet weather events is only going to help with respect to understanding the end game. And at the end of the day, in addition to every wastewater treatment plant being different, the challenges that each wastewater treatment plant see during wet weather is also unique. And so there's no one single solution. But there are tools in the toolkit that a collection system or that a utility can look at. And we'll talk through some of these, the first being the collection system. Obviously, the biggest focus is how can I reduce, or how can they reduce infiltration and inflow? When I get an influx of flow, is it additional sewer maintenance? Is it additional rehab? Is there opportunities to increase capacity, whether that be within the network itself or on site at the wastewater treatment plant? And are there opportunities to control those flows and provide some flexibility with what and gets, what ultimately ends up getting delivered to the wastewater treatment plant. Storage is also part of the solution. Is their ability to take advantage of either on-site existing storage, implementing it within the collection system, what have you. But storage allows you to shave off some of those peaks and really limit, the ultimate peak flow that may end up at the plant. There are challenges with both. Obviously, the collection system, as we talked about, is complicated. It's costly, and it's often a never-ending endeavor, as I mentioned earlier. Storage has its challenges as well, right? There's ancillary equipment that must be considered, pumps. How am I going to maintain it? How am I going to clean it? Do I need odor control? How big is it? The construction aspect of that. But it's a finite capacity as well, and it's going to be impacted potentially by future flows and future growth in the community. And at the end of the day, in most scenarios, what you find is collection and storage are part of the solution, but they're not the end-all be-all. There has to be additional steps, and that's when we transition to looking at the water treatment plant itself and looking at ways to, can I improve the efficiency, whether hydraulically or performance-wise, or can I increase capacity, whether it be additional trains, increase redundancy, what have you, but that's always an aspect that gets looked at. And then another debated topic is green infrastructure. Dealing with the stormwater flows, and rather than relying on the impervious surfaces, can you implement surfaces that are designed to soak up that water and limit the amount of water that ends up in our sewers with natural areas, swales, green roofs, and what have you. So again, all part of the overall picture and many tools that a utility or a municipality can rely on. So looking at some of the treatment options, when we talk about what a treatment facility will look at with respect to on-site performance, conventional clarification, you're typically talking conventional clarifiers. Oftentimes there's maybe an ability to re-rate those or enhance them, say with chemical addition and kind of converting it to CEPT. Plates and integrating those is potentially another option. Not done a lot here, in the US, but it has been done with some success overseas. Vortex separators, even new technologies such as primary filtration even. So lots of things to consider and evaluate when a utility goes through this type of scenario. And then from a secondary perspective, are there opportunities to increase capacity, add on additional trains, make use of what's there and just make it more efficient. And that could include the way you control your secondary basins as well, whether it be step feed or implementing scenarios that allow you to settle solids throughout the length of the basin to help increase the hydraulic capacity a little bit during those peak flows to help avoid any biomass washout. And then I want to shift gears just for a little bit and talk about some of the advanced treatment steps that have been proven, especially here in the US and globally, as part of an overall solution to help facilities minimize overflows. And that is enhanced high rate clarification, as well as biologically enhanced high rate clarification. When we talk about enhanced high rate clarification, we're talking about a physical chemical process that uses your standard coagulation flocculation process that have been around for decades. And so it's taking that chemistry aspect and enhancing it with a ballast, and in this case microsand, to really act as an anchor. So you develop the pin floc and the flocculated material, and then you just tag an anchor onto it, and it settles out like a rock. And it's this efficiency that allows for a very short startup time with respect to the process, which is very important from a wet weather, being able to react in a timely manner. But it also means very high surface loading rates in terms of 50 to 70 gallons per minute of treated capacity per square foot. So a very compact footprint, oftentimes works well in plants that have limited footprint available, and it helps reduce overall project costs via the construction aspect. And because of the ballast and taking advantage of that coagulation flocculation process, enhanced high rate clarification is very efficient in terms of TSS capture, and really anything that can be coagulated and removed, including particulate BOD. The challenge becomes the soluble fraction of that BOD, and that's where enhanced high rate clarification, it really becomes limited in terms of when you consider secondary standards and meeting TSS, but also total BOD capture. As a result, we put a lot of time and effort into developing biologically enhanced high rate clarification to help solve that challenge. And it pairs contact stabilization with the same enhanced high rate clarification that we previously talked about. So two proven technologies combined together to really focus on not only TSS, but total BOD. And the way it does that is it utilizes an upstream contact stabilization basin and takes advantage of the excess biological activity of a plant. So it's going to borrow a very small side stream of RAS from the main plant, mix it within the influent stream, and really afford any soluble BOD to uptake and absorb onto the mixed liquor to reduce that soluble fraction before that mixed liquor enters into the high rate clarification step, again, for efficient settling of the solids and allowing biologically enhanced high rate clarification to meet secondary standards with respect to total TSS removal as well as total BOD removal. And because biologically enhanced, well, really both enhanced high rate clarification and biologically enhanced high rate clarification can operate from the very beginning to the very end. It can operate at high flows and low flows. It can see and handle the peak solids, and it can handle the dilution on the backside. And that's a big advantage for high rate clarification. Biologically enhanced high rate clarification takes it a step further because it can meet those secondary standards. It can do it without blending that water back in with the main plant. And that really can provide a level of confidence for operators. They got enough going on during a wet weather event. Relying on a system that can just do what it needs to do to meet permit, it's got to provide a lot of operational flexibility. So taking just a quick look at kind of how these fit within the process flow of a plant. First, on enhanced high rate clarification, again, peak excess flows beyond the capacity of the plant, diverted around, send it directly to enhanced high rate clarification. Again, focused on TSS removal, particulate BOD removal, phosphorus, and then that gets clarified, effluent sent, it's then blended back in before disinfection. Any solids captured, then either sent to the head of the plant or to existing solids handling facilities. Again, this is typically your combined sewer type setups. And in this case, enhanced high rate clarification can be either in parallel to the main plant or located out in the collection system. Looking at biologically enhanced high rate clarification, again, very similar principle as we just talked about with enhanced high rate clarification, but it combines that clarification system with the contact stabilization basin upstream. Again, peak flows diverted around the plant to protect, whether it be the primary clarifiers or the secondary basins. Those peak flows diverted around. And again, we're going to borrow just a small side stream of RAS, blend it in with the influent stream, and essentially just kind of mix everything within that contact tank and allow contact associated of the mixed liquor with the influent stream to absorb and to uptake that soluble BOD onto the mixed liquor, reducing the soluble fraction. And then this carries through into the efficient clarification step of enhanced high rate clarification, where we get the solids removal, the solids coming on the influent stream as well as the mixed liquor and RAS, before, allowing the system to meet not only greater than 85% of TSS removal, but also greater than 85% removal of total BOD as well. Of course, RAS is very important to the main plant. So again, we're only borrowing it. We're constantly, as it makes its way through the process, we're constantly discharging that RAS back to the secondary system for reuse and regeneration. So again, just kind of works like clockwork. That RAS is not in the system, but for 20 to 30 minutes at most before it goes right back on a continuous basis back to the main plant. So looking at some of the differences between performance, as you can see, both systems are very efficient in terms of TSS removal. The BOD is really the difference here. As I mentioned, it's all dependent on that soluble fraction of BOD. And while you will get some total BOD removal, primarily the particulate fraction with enhanced high rate clarification, in order to meet secondary standards, biologically enhanced high rate clarification is needed, again, to uptake soluble BOD, reduce the soluble fraction, and therefore allow you to meet both total TSS and total BOD. Obviously, both processes are very efficient in phosphorus removal as well as UV transmittance and disinfection, which plays into E. coli removal as well. So Real quick, just wanted to highlight the references here in the US. This is just focused on the US. There are many more installations globally as well in the wet weather application, but there are 33 references here in the US for wet weather treatment. The color code here, the light blue is our CSO facilities for enhanced high rate clarification. The dark blue is SSO facilities with enhanced high rate clarification, and most of these are prior to 2010. Essentially after 2010, everything has been of the biologically enhanced high rate clarification aspect, and those are your magenta or purple colored. So shifting a little bit now to talk about some examples of what we see of what we've seen with different municipalities and how they've handled not only identifying their challenges but how best to manage them. So the first facility I want to talk about is in Knoxville, Tennessee, operated by Knoxville Utilities Board, and then again partnered with CDM to really evaluate their treatment step, their collection system, due to a 2005 consent decree issue, with the goal of essentially eliminating SSOs. KUB, or Knoxville Utilities Board, operates 4 treatment facilities in the area. Kauai is one of the larger facilities, and Fourth Creek, identified here on the picture on the right, is the 2 facilities that were really focused within the consent decree. Obviously, with the consent decree, the requirement for a composite correction plan is required. And so again, coordination with CDM and their efforts, they went through a pretty exhaustive evaluation. And it started with comprehensive performance evaluation. And that really is focused on identifying the weak points like we talked about in the wastewater treatment facility and the collection system. Understanding what the limitations are, where the weak points are, what's the likelihood that they'll fail, and understanding at what point will a SSO or diversion occur. So, through that evaluation, that then gets fed into obviously the composite correction plan. Same with the process control plan, which is kind of identifying not only the strategies that they used, during the consent decree time period, but strategies moving forward to better improve their operation during a wet weather flow. And so all the weak links, all the areas for improvement, that goes into your composite correction plan. And it, again, identifies the limits of the wastewater treatment plan. It addresses the procedure for handling those peak flows, and it sets an action plan and a schedule to correcting those factors. And the Knoxville Utility Board was, again, focused on SSOs, and they were focused on what they defined as a 2-year, 24-hour storm. So that really kind of set the stage for them to understand, all right, now that we understand our problem, how do we move forward? So this correction plan identified a number of hydraulic and process control challenges. And as a result, they looked at it from a holistic perspective and focused on kind of 3 key areas. The first, obviously, is the collection system. How can we reduce the challenging issues within the network, reduce our I&I, and help us reduce the overall load and flow to the plant? So they looked at a number of things. They looked at pump station upgrades. They looked at opportunities for rehab and repairing pipe, as well as upsizing pipes to increase the capacity. They also implemented a maintenance program where they basically assessed and identified areas of repeated issues. They looked at restoration plans for removing and fixing those issues, as well as pipes that have built sediment up or debris up over time, and then a repair plan to, again, once you've identified those areas, going in and replacing issues that are due to the wear and the corrosion and the overall age of the collection system. They also looked at storage as well. The Fourth Creek facility, I think, had some limited storage, but they focused heavily, at least from a storage perspective, on the Kauai facility. Kauai is a much larger flow, I think projected upwards of 120 MGD peak wet weather flow. And so storage there was more beneficial for them to help shave off some of those peak conditions and limit the amount of flow that they'll have to ultimately treat at the plant. What they found, at least through this initial effort, is that the collection system and the storage system alone aren't enough to address the challenges. And so they also then focused efforts on how can we improve our existing wastewater treatment facility. And they looked at a number of things and did an evaluation, not only considering capital costs, but also construction costs. But most importantly, what is it going to take and what is the impact on each of these systems on capacity and performance? So they looked at CEPT. They also looked at enhanced high rate clarification as well as biologically enhanced high rate clarification. And they did a pilot in late 2009 and 2010. And ultimately arrived at the conclusion that CEPT and enhanced high rate clarification by themselves were not capable of eliminating SSOs and consistently meeting their permit, which were their primary goals. So now shifting kind of just to the Fourth Creek facility, and the reason I want to do that was the first installation installed. And the reason the facility did this, as I mentioned, Kauai is a much larger facility. It's crammed in the middle of downtown Knoxville up against the University of Tennessee. It has a road going down the middle of the plant. And so because of its size and because of its complexity, they wanted to kind of work out the kinks, so to speak, of construction, of integrating biologically enhanced high rate clarification before they then went and focused on the Kauai facility. So in 2014, at the Fourth Creek facility, they implemented just enhanced high rate clarification, gave the operators a chance to get familiar with the system, again, working through the kinks of construction, and then they converted to biologically enhanced high rate clarification in 2018. Some of you on the call are in the Southeast, much like myself, the entire area, it seemed like, got dumped on in late 2018 and 2019. Record rainfalls, especially in Knoxville. You can see, just in February alone, the Knoxville area received 4 times their 10-year average in terms of the amount of rainfall, widespread flooding that lasted for days. The utility itself, treated over 4 billion gallons of water, which is, a greater than 30% increase from years past. But what we found, and you can see through the data here, that biologically enhanced high rate clarification, again, in addition to the other improvements they made, was able to solve their challenges and eliminate those sanitary sewer overflows. And so you can see with the influent characteristics, and I guess this operated 14 events over that, roughly 3-month period. And you can see the effluent criteria less than 10 TSS and total BOD across all 14 events. Switching gears a little bit now to Lawrence County, Newcastle Sanitation District, teaming up again with AECOM in response to a 2011 consent order. Their goal was obviously eliminating bypassing if flows greater than 18, and that is their secondary treatment capacity hydraulic limitation. They do see peak weather flows upwards of 38 MGD, but secondaries really were the primary concern. AECOM worked with the district, again, to understand the problems, right? So challenges of peak instantaneous flows. They also see sustained high BOD and TSS loadings during these events. They also deal with a very complex and convoluted network, very vast. They, support surrounding cities and townships in dealing with those wet weather issues. But oftentimes they don't manage or control those sewer systems. There's a lot of collaboration, a lot of effort needed to maintain the sewer networks. And the age of the facility also played a role. Not only is it reaching its end of treatment capacity, but it's just not as efficient. They also have a lack of redundancy, especially in key areas that, when something went down, it kind of compounded their problem. So once they kind of understood the challenges, they looked at a number of things, and we'll talk about those in the next slide, but they did look at expansion at the wastewater treatment plant with their conventional system. They also looked at side stream treatment of that peak flow with ballast clarification as well. And so it was a staged approach for them. They started in 2015 with a 1 MGD EQ basin to help, mitigate some of those peak flows to the plant. They also put in a stormwater management program in 2018. It focused on the obvious, right? The repair, the replacement, identifying the challenges. Can we put in additional stormwater lines, repairing where necessary, especially with stormwater manholes. Again, talking about additional capacity, where can we add it? There was a lot of talk and a lot of integration of that. But they also invested in tools to help them manage and identify where they needed to focus their effort. So they invested in sewer cameras and cleaning trucks, really to help operation and maintenance of that collection system. And from a wastewater treatment perspective, they're looking at a number of things. This project now, from a wastewater treatment improvement perspective, is currently under construction. But they're looking at converting, again, another digester to a wet weather EQ basin for wet weather, but also a pumping station that will send flow to the biologically enhanced high rate clarification system. They're looking at improving the split of flow between the primaries. As you saw, the primaries have a higher end capacity, but not quite covering the 38, and they'll help, hoping that this improved flow split will help the primaries during those peak weather events as well. Talked about redundancy. Solid handling system was one of them. They put in some additional redundancy, and as well as plant expansion with their aeration and secondary clarifiers as well. We did some on-site jar testing in 2018, really from a training perspective, a validation perspective, but also to quantify the OPEX as well of the biologically enhanced high rate clarification. And hopefully, like I said, under construction now, and hopefully online and commissioned in late 2022. Shifting to our last reference point here, City of San Mateo teaming up with HDR and Brown Caldwell due to, again, a 2009 cease and desist order, again, with the focus of eliminating those overflows and blending associated with wet weather. A couple of PERs were done via CH2M Hill and Carollo. The first one in 2014, it was amended in 2019. Very similar challenges, right? The hydraulic challenges associated with the network, associated with the collection system, and unique features as well. Their collection system, very vast. Again, they have the similar challenge of surrounding communities and dealing with who's responsible for what. But also, a majority of their collection system was built in the early 20th century. And due to the standards back then, many of the pipes are less than 6 inches. They're prone to plugging even in dry weather flows, but also they were built in very short segments. And so you can imagine, essentially, if you've got joints and those joints are the weak points. And so you've got lots of joints now that potentially are failing, reaching their limit of age, and potentially increasing the I&I associated with it. At the wastewater treatment facility, obviously very similar challenges in terms of age. It was built in 1940. It went through a majority of its upgrades and repair of equipment up until about 1980. So the majority of the equipment on site now is greater than 30 years old. The secondary capacity is limited to 40 MGD currently. And based on Carollo's effort in 2014, they do project a peak wet weather flow of 98 million gallons a day. Another unique aspect of this is the outfall capacity. The city is limited to a hydraulic capacity at their outfall of 60 MGD. So again, understanding all of that really helps tailor, the solution moving forward. So what did they do? Again, collection system focused, focused on, sewer repairs, also capacity increases, whether it be pump station upgrades or adding and rehabbing existing relief pipelines. A lot of their sewers are in right-of-ways, and so there's an impact to businesses and roadways, and so they were looking at ways to integrate relief pipelines to alleviate some of the challenges. They are integrating storage, 8 million gallons of storage, both on-site as well as out in the collection system. That will reduce the peak flow by about 40 MGD. Again, that comes with the ancillary equipment that we talked about. Due to Title 22 standards, they are converting to IBR, and they did evaluate Bioset versus biologically enhanced high rate clarification. Bioset is kind of a dual primary clarifier that can operate both dry and wet weather. And what they found through an exhaustive evaluation is that biologically enhanced high rate clarification can save a pretty significant amount on construction and excavation. And so biologically enhanced high rate clarification is selected, and that one should be online in late 2022 as well. Because they're transitioning, obviously there's a function of rehab and repair to the existing system, again, to maintain operation while they're building the new facility. And then the strategy aspect of helping the operations staff and putting a plan in place when wet weather happens. So with all that, my takeaway, right, is, the impacts of wet weather are not only challenging themselves, but the hurdles that municipalities deal with during a wet weather event, and finding the best way to navigate them is the biggest hurdle, is the biggest challenge. Obviously, the severity and the frequency of storms, urbanization plays a large role now, especially in large cities, and then the aging infrastructure and the costs associated with managing all that. As I mentioned, comprehensive evaluation is absolutely key. Understanding the risk and the failure points, the likelihood that they'll fail, what will happen when they fail, and really, make sure you understand the problem before you put forth a solution. And then the solution can look like a number of things, but a lot of the time it's focused on kind of key 3 areas: reduction of, or I should say, reduction of I&I and maintenance of that sewer system. Oftentimes that's an operation and maintenance incentive plan to really drive improvements within the collection system and maintain that capacity. Storage is a key player as well to help shave some of the peaks. And then increase treatment capacity, and advances like biologically enhanced high rate clarification have shown and are well established as a proven component to any overall solution that a facility has to manage. So with that, I appreciate the time. We're running a little bit late. I apologize for that, but I appreciate the time, and hopefully you found this very useful.
Great, thank you very much, Reed. I just want to remind everybody, and I apologize, I forgot to mention it at the beginning, but we are recording this webinar, so it will be sent out to you. The recording will be sent out to you within, I believe, 24 hours or so. So do feel free to watch for that. And also want to remind anybody to ask any questions that you have, to type that over. And with that, we do have a couple minutes here that we have some time for some questions. So we'll try to get through as many of these here as quickly as possible. But if we don't get to your question, I apologize for that, but we will reach back out to you directly to answer those as well. So with that, I will open up our Q&A session. Reed, one of the questions that we have here is, how much RAS is required, and also what impact is there when returning it back to the existing biological process?
Okay, good question. As I mentioned, biologically enhanced high rate clarification is just borrowing RAS. When you consider the influent flow to the biologically enhanced high rate clarification, the amount of RAS is, and it can vary based on what you're trying to achieve, but anywhere from say 7 to 12% of that forward flow. And as far as impacts, again, we're constantly bringing that back to the main plant. Really, the only impact is the minor amount of additional solids created through the coagulation step. And you can imagine the coagulation step is going to generate some additional solids, but it's a very, very, very small percentage of the solids that essentially we're maintaining within the process. We do try to maintain anywhere from about 500 to 1200 milligram per liter of mixed liquor within the process. And you can imagine those additional solids are kind of a drop in the bucket. So the majority of what gets sent back is the RAS, and what we've seen is there's really no impact to the biological process.
Great, thanks. We'll try to get through maybe 1 or 2 of these more questions that we've got. How much operational flexibility does biologically enhanced high rate clarification have in handling wet weather flows?
Yes, so those familiar, and as I tried to explain, through the presentation, biologically enhanced high rate clarification takes advantage of enhanced high rate clarification, and so with that, they get the optimization and flexibility of optimizing performance based on influent conditions through minor adjustments in the chemical feed, coagulant first, and then polymer. In addition, biologically enhanced high rate clarification has the ability to adjust how much RAS you borrow. So based on a given activity of that RAS, you may need less RAS or more RAS, and so you can adjust that RAS concentration based on influent conditions and your target effluent conditions. And I think the key advantage for biologically enhanced high rate clarification is it really can operate from the very beginning to the very end of an event. There's no worry about how much flow you see or how much solids. The system will handle all of that. And it really gives that operational flexibility to not worry about that process, to be able to meet that secondary standard without having to rely on how the main plant's performing.
Great, thanks. We'll close out here with one more question that we've got, and I do apologize for going over, but we do appreciate for those of you that have stuck around. How does biologically enhanced high rate clarification performance during wet weather, how does that compare to that of the main plant?
Yes, as we showed through the data, and those that are familiar with how secondary traditional wastewater treatment plants operate, able to get, greater than 85% removal of TSS and BOD is going to put it in comparison with the main plant in terms of their performance during that wet weather event as well. There's been side studies done. Akron, Ohio is a specific example where not only it was a study to evaluate biologically enhanced high rate clarification's performance, but it also compared it to the main plant during 20 wet weather events. And at the end of the day, what it concluded is that biologically enhanced high rate clarification meets and or exceeds at times the performance of the main plant. So again, it can do just what the main plant does in terms of TSS, BOD, pathogen reduction, and produce, an effluent that is easily disinfected. So very similar.
Great, thank you very much, Reid. And that concludes our webinar for today. We do very much appreciate your time and taking your time to spend with us today. Just a quick reminder that if you would please fill out that survey, that would be greatly appreciated for that. And if for those of you that do, you will be entered into a drawing for a chance to win a $25 Amazon gift card. So if you are the lucky recipient, we will follow up directly with you for that. And please feel free to check out the website www.veoliawatertech.com to check out any upcoming Veolia Water Tech Talks, as well as those on demand. So with that, we do thank you very much for your time, and we appreciate it. Thank you.
Thank you.